Equivalent circuits provide a powerful framework through which we can conceptualize problems in heat transfer and also solve them more quickly. So for one-dimensional heat transfer through a slab, we can find that the heat current is Q equals minus delta T divided by a quantity L over Kx times A. This is sort of a glorified statement of Fourier's law. This statement is really simply that a current equals a driving force over a resistance. Current is heat current, a driving force is a temperature difference, and this quantity in the denominator is really like a resistance because it is the inverse of a conductivity with appropriate length scales. A conductivity describes how easily heat moves through a system, whereas resistance tells us how easily heat is stopped or blocked. So it makes sense that there is an inverse relationship between a quantity that describes how easily heat moves through a system and how easily heat is blocked in a system. We can draw an analogy here to circuits. This equation just begs for an analogy to circuits. Current is like electrical current. The driving force is delta V, a difference in voltage, and we have a resistance, which is the conventional electrical resistance, R, in the denominator. And so we see here then that the statement that current equals a driving force over resistance is true not only in heat transfer, but is also true in circuits for the statement of Ohm's law. So any object through which heat moves, we can conceptualize that as a resistor, which has a resistance R, because that object is resisting heat transfer according to Fourier's law. And with this analogy, we can draw an equivalent circuit for one-dimensional heat transfer in a slab. So let's say we have a slab which is held at a temperature T1 on one side and T2 on the other. We can instead just say that this slab is really a resistor. And in this resistor that we have here, we have a temperature T1 on one side and a temperature T2 on the other side. We can characterize this resistor as having either a resistance R or a resistivity R double prime. The resistance is a quantity which leads to the heat current, while the resistivity is a quantity that leads to the heat flux. Underlying all this is that the resistance is a quantity that depends on how much material there is, whereas a resistivity has normalized all this out. So we define then the resistance R as involving R equals L divided by Kx times A. We can see that simply by comparing the quantity for heat transfer to what we have over here for circuits. We can then take that resistance and use that to get to a heat current. That a heat current equals a negative of a temperature difference divided by a resistance. This is really just a restatement of what we saw up here. We can similarly then take this resistance R right here and determine a corresponding quantity R double prime, which is simply taking that resistance and multiplying by A, the area, in order to get this value L divided by Kx, which is our resistivity R double prime. If we take R double prime, it turns out that it is what is needed to satisfy this equation here, that Q double prime equals minus T divided by R double prime. This is then the definition that leads to the resistivity R double prime, that it is this quantity that is useful in a flux-based expression. So we can define then R and R double prime based on the last expressions shown here for heat current and heat flux. For electrical circuits, it's common to consider this configuration of resistors in which they are in series. And we're going to do the same thing now for heat transfer by considering slabs which are in series. Imagine we have slab A, which is next to slab B. Slab A has a thermal conductivity of K sub A, and slab B has a thermal conductivity of K sub B. Slab A has a thickness of L sub A, and slab B of L sub B. The temperature at one end is T1, all the way on the other side it is T sub 3, and at the interface of the two slabs we have a temperature of T sub 2. Because the thermal conductivities of these two slabs is different, while the heat flux is the same, that means that the gradient dt dx must be different in each slab. And you can see that here based on the slopes that we've drawn in slab A and in slab B. We can create an electrical circuits analogy. So we draw out this circuit diagram where we have T1 at one end, T3 on the other, and a temperature T2 in the middle. And there are resistors that connect these, a resistor for slab A and a resistor for slab B. The resistances of these slabs are given by the expression that we just introduced, that R sub A equals L sub A divided by K sub A times A, and a similar expression for slab B as well. For electrical circuits, when we have resistors in series, we would just add those resistances up. And the same thing is true for heat transfer as well, that the equivalent resistance is given by R sub A plus R sub B, and hence we have this expression here once we factor out 1 over A. The heat current then is given by the expression that we introduced just a moment ago, that the heat current equals negative of a temperature difference over the resistance. And because we're now going to plug in with the equivalent resistance, a resistance which describes the entire system, slab A and slab B, this then means that the temperature difference that we plug in here must be T1 minus T3 over here. We can get this exact same answer for the heat current without using equivalent circuits at all. We could just solve the heat diffusion equation and go through the usual process of applying boundary conditions and get to a solution. Equivalent circuits are simply a shortcut that helps us get there more quickly. We want to now take everything we learned about equivalent circuits and use that to understand the concept of interfacial resistance. The very simple question that we want to ask is, can temperature be discontinuous at an interface? Imagine again that we have two materials in contact, slabs A and B, but this time here at this interface, we have temperatures T2L and T2R. T2L is the temperature on the left side of this interface, and T2R is the temperature on the right side of this interface. Local equilibrium implies that this should not be possible. This is because the two materials in contact should be equilibrated and hence should be at the same temperature at that interface. However, if there is an interfacial resistance, because there is a microscopic gap or imperfect contact between slabs A and B, then we could in fact have a different temperature on each side of the interface. Drawing out an equivalent circuit clarifies the physical picture here. This means that if there is a contact resistance or an interfacial resistance, that we need to have 3 resistors, not just 2, as this diagram may otherwise imply up top. That we need to have one resistor for slab A, another resistor for slab B, and another resistor for this interfacial resistance. Only by having a resistor there at this interface do we have something which is able to impede heat transfer and thereby create different temperatures on each side of this interface.